Chen, and he's from SOLVCON, and he is also the chief organizer of this very session for SciPy. So please give a very big hand. Thank you.
Yeah, thank you. Yeah, it's really a pleasure to be able to be here and to speak something about solving partial differential equations. So I suppose everyone here are a big fan of equations, right? So how about tell me that what's your favorite equations? Anyone? I love that too, yeah. But it cannot be time matched, right? what's a pity? Anyone else? Oh, because I'm from CFD, so yeah, Maxwell equation is good as well. And Navier-Stokes equation is just awesome. Okay. SOLVCON is a package that I wrote for solving partial differential equations, but to be precise, actually hyperbolic PDEs. I am trained as an engineer that uses computers to solve problems in mechanics, fluid dynamics, solid mechanics, and even electrodynamics are all in my interest area. I want to solve a lot of them, and I want to solve equations for various physical phenomena, so that I wanted to create or to develop a software framework so that I can do them productively and hopefully efficiently. So these are the examples that I have done. Excuse me, that didn't include Maxwell equations. But this is for some gas dynamics computation, and there's some simulation of solid wave, stress waves in anisotropic solids, and this is yet another more complex fluid dynamics calculation. My goal is to solve equations that take in this form, especially the left-hand side, which is the quasi-linear form of hyperbolic PDEs. I chose to use the space-time conservation element solution element method, which basically is a finite volume based method, and with a nice feature that I don't need to have the Riemann solver. And that's part of the reason that we want to have an extensible system so that we can modularize the software to use various physical processes, because we kind of want to know that what we can really do for this numerical method and try to use that feature, use that phase agnostic feature to create a software. And it is also a norm to use parallel computers to do computation for this kind of simulations. And 1,000 core should be a reasonable amount for some problem that started to be interesting. So that's the goal we are shooting for. We also want the code to be organized so that we can really grow that software someday into something that can be used for anything like research or even for industrial use. So it seems to me that it can an engineering problem. Oh, by the way, I wrote SOLVCON while I was pursuing my PhD several years ago. But I realized that it's actually not, of course it's a research project, but the essence of it is how we are going to organize this software, these computer programs, and to deal with problems that we really want to know. And we really want that once some graduate students graduate, this code can still survive, and someone else can pick it up and to further improve that. So the focus of this work is the following things. It's the extensibility and modularity, it's parallel computing, and it's how we are going to maintain the code. So far that since I have graduated, so I claim that all goals are met. But still, we have a lot of rough edge that we need to clean up. And the more I do it, I found that it's really a very, very difficult problem to do. But right in the center of this answer is Python. You may be surprised that I wrote Python is slow, and I use it to run high-performance computing that utilizes thousands of CPUs. But the point is that Python is very good to form an infrastructure so that you can tap into all different kind of functionalities into the computing system. Two important things. One is the NumPy array. NumPy is a numerical Python package that allow you to do a lot of numerical operation as well as linear algebra. It is a very efficient implementation for arrays, and array is the center of all HPC code. The other thing is SISAM, or in general, the way for you to make C or C++ to talk to Python and vice versa. So those two things are important because we need to get all this system work, and we need to have high-performance, low-level code written in C, sometimes even in assembly. And the Python ecosystem, like what Wes McKinney has mentioned this morning in the keynote, like SciPy, IPython, and various packages, allowed us to really build a system for free. Free of time, actually. There's a lot of functionality that we need in those packages. And you cannot even buy them from anyone. And we also want to use, we know that in universities that few people are practicing software engineering in traditional engineering or scientific departments. But we need to work like a professional and software engineer so that we can make this really a software that can do work. And another reason for us to use Python is that to carry out analysis, actually you need to write scripts. You don't write Java or C or C++ code to analyze your data. You write something like a MATLAB code. You write something like maybe like R or right now Pandas or any other high-level tool. And many people are using Mathematica, are using Maple, right? It doesn't matter if they are free or they are charging. But the point is you need some high-level tool to do your analysis. And Python can just be the answer. You use that to form your computing system and do that, and use that for your analysis. So that by combining Python and all the rest of the world, you really have a system that deal with productivity. You do your things just in time with acceptable efficiency, runtime efficiency, and you have the full flexibility to further improve its speed later on. That's what we are doing. So we come back to the technical part of SOLVCON. There actually are two fundamental concepts in the system. The first is that because we are solving partial differential equations, and we want someday to be able to be applied in the industry, so we chose to discrete the space. So it's a grid-based or mesh-based software system. And I think everyone of us know or have heard that in the macroscopic world, everything is continuous, right? Like everything that you are touching, you don't expect you can touch the atoms. No, you are touching objects. But in computers, actually, we need to create everything discrete. Computers do not know anything like continuous. So this is the result that I have shown you. You see then like some lines and something, but they are really contours from some discrete field. So this is the way in SOLVCON we discretize the spatial domain. We want to accommodate the most complex possible geometry, so that we chose to, in 2 and 3 dimensional spaces, we use unstructured mesh or off mixed element. Currently, we have 6 of them, 2 in the 2-dimensional space and 4 in 3-dimensional space. There could be more, but in general, these elements are sufficient for discretize your space. And doing this unstructured mesh approach is nice. But before we can have the niceness, let me say that for parallel computing, we need to have the data structure. In general, in SOLVCON, or in general in most of the unstructured mesh data structure, they are using lookup tables. And there are 3 categories of those mesh lookup tables. The first is storing coordinates. The second is storing some metadata. The third is connectivity. So unlike structured mesh or Cartesian mesh or Cartesian grid, you know where your grid point really is, or in the graph, in the relationship to each other. For unstructured mesh, you really need to remember all this information for you. So that creates a lot of overhead, but also gives you flexibility in geometry. And we use ghost cell technique. We are not going to detail about that, but that's how we are creating boundary conditions. So life can be much easier if we don't need to consider boundary conditions. But we know everything has a boundary. And in computer, you cannot have unbounded domain. So we need to create a boundary condition. So that's how we do it. Basic ghost cells are just some elements that are outside your computing domain. So the niceties of using the unstructured mesh is one of that is you can have a very flexible parallel computing decomposition. So when we get the mesh and we have all the elements, then we can we know is connectivity, so that we have their connectivity as a graph. Then we can just partition the graph. There are existing packages, very good packages. We just partition the graph. Then turn it back into multiple blocks. Then we can just put them on different nodes and do computing. And because we have the ghost cell can also act as the interface between all those blocks. So that's one of the foundation of SOLVCON. The other one is loops. Basically, equation solvers are just a lot of loops. We just loop over 2 things. One is time. The other are space. So we do time march as the outer temporal loop. One by one, one by one, one by one. And inside that temporal loop, we have a lot of sweeps for our spatial domain, and do the processing and process all those arrays and get the answer, and maybe we can do some check. And this structure, around this structure, we form the whole architecture of SOLVCON, because you cannot escape from this 2-level nested loop structure. So every other logic should be around this concept of nested loop. The core of that nested loop is here. And let's see this diagram. We have a case. Yeah, in the system it's called the nest space is this. It's a mesh case because it's a abstraction of a spatial loop that utilized for unstructured mesh. So that's the name. It's outside and it will do temporal loop. And inside the case, we have mesh solver, which is responsible for spatial loops. there usually are a lot of spatial loops, because for one time step, for one time marching, you just need to do a lot of processing. And as you can see that we have two nodes here. So this structure automatically gives us a parallel computing infrastructure or structure. We can just have a head node working on or operating on the temporal loop and commanding the solver which housing the spatial loop. And if you are smart, if you have experienced that, you know there's a bottleneck here. But that's a general structure that even if you want to remove the bottleneck over here, we still need something some structure like this. And based on these two-level nested loops, here comes a question or a solution actually. We want to solve PDEs for really high resolution answers. And let's see this simple calculation. Say we have 50 million mesh elements, and we want to run 10,000 time steps. Anyway, it turned out to be, if we store everything on disk, it will be 12 terabytes. And you don't want to store that, right? Unless you are the SSD manufacturer. So one way to resolve that is trying to do the analysis when you are producing these solutions, right? When you are producing all these arrays and you just do analysis on the fly. But the problem is that then you have a bigger software engineering problem that you need to segregate well about your analysis code from your simulation code. And that is very difficult. But if you don't do that, actually your code will very quickly become unmaintainable. So most of people chose the other way. Is that, okay, maybe the simulation can be very high resolution, but maybe the answer we want or the analysis we want to carry out does not need that high resolution. So they just output every 100 time step or something like that, and maybe it can compress the spatial domain and to get count 5 element into one and output the solution. They are all viable ways, but actually it just defeats the purpose of running high-resolution simulations. So I really want to solve this problem, but as I said, it's very difficult. So in any way, our approach is that, like what I show you in the structure diagram, we not only have case and solver associated with the temporal loop, the mesh case class, we have associated hook class, so that we do, it's a very minimum segregation of logic, but we do computation of analysis in the hook class, in the outer loop. And we have an anchor class, which is associated with the solver class that do the analysis. So actually, there should be a dash line between hook and anchor. Sometimes they need to talk to each other, but I haven't figured out how is the best way for the communication pattern or for the communication infrastructure. It's we have some demo for this kind of structure, but it's very difficult to use that in the production. Yeah. So that's basically is the fundamentals of SOLVCON technology, and you may think that's easy. That's really easy for those two parts, but I have to confess that I actually have made the code base pretty messy, and there are a lot of details need to be considered, like how to work out the parallel computing and how to come up with a portable communication layer. And I made some really bad decisions, as well as some really good decisions. But to go on, I think what's more important is how we should make this thing sustainable and to address extensibility, maintainability, and parallel computing altogether. Because we are dealing with scientific research or scientific computing, so the problem we are solving actually itself is pretty complex and need a lot of explanation and maybe teaching or training. So I really think that in SOLVCON, we should just contain what we usually publish on journal paper or conference papers. Without doing that, actually, it will be very difficult to do cross-reference for what you are doing in the code to what you really want to do as the formulation. So right now, I'm choosing use things and read the docs and to write the document like this. Okay, this basically is just the homepage of SOLVCON, and I created Sphinx. Actually, I think I have a full website. Oops, it's not allowed me to do that. Yeah. So it's a homepage of the software, and of course, the computation is far from complete, but you can click anything. Oh, it's my local host, but doesn't matter. It's on the website it's of the same thing. So I just use Sphinx to do all this documenting and trying to make things consistent. Okay, and we use Mercurial and Bitbucket because I really like I can have anything with Python, and Mercurial is written in Python, so I don't like GitHub. Yeah, no, just kidding. And we can just review our work by going through the normal peer review or pair programming pull request flow, and use restructured tags, which is really easy to work with to do things. And the other thing is, which is important for the development, is do testing. And in my experience, that at least in for engineer or conventional engineering practices, we don't understand or we don't know so much about testing software. There is kind of a strange mentality that when we write the software and it runs, it should be right. But we all know that's not true. So the true thing is that if you don't verify things, you don't run that to get some really validated answer, you do not know your software is running correct or not. So you need a very extensive and overarching covering test cases. And in SOLVCON, because usually by the way, the example, the 12 terabyte examples I show you, I actually had a 66 million mesh point run several years back, which took me 2 days to run, and using the in-situ visualization technique for doing the analysis altogether. And at that time, actually, I've heard that someone somewhere actually did simulation for 30 million elements, which using another code, and he spent several days to generate the results, as I did, but a quarter or two to analyze what it did. To visualize what it did, because his visualizing tool is sequential; it's not parallel. So he need to load all those data to a really giant workstation and try to visualize it, which just almost killed him. So it's really a time-consuming thing. So it's not realistic for us to carry out that kind of verification every time we commit the code. So we need to separate them. So for easy tasks or for something that we can really know the answer, we do unit test. For something larger, we do answer test. But for something practical, like some tens of millions of elements, I don't know how to do that yet. But I know that there's a tool we're using. There's a unit test, node test. And on answer test, we have a Jenkins. And we have a server farm, which have only one server. So this is the challenges that I want to express to you. That I have been working on the code for several years, 4, 5, or 6 years, I can remember. And there are some generations of that. So I actually was suffering from the old version. Some of my collaborators actually was staying on the old version. I don't know what to do. And that's hurt. But I'm going to work on that. And a lot of people who are not familiar with the new generation of documenting tool from, we can say, the old school engineering practice. And we need to have a lot of communications so that we can really get this right. And because our goals are shooting for a lot of physical phenomena, so there's another work that we need to get the lesson learned from that individual problems into the general framework. And also, server farm is a very, very serious problem. And does anyone have extra computers? So that's pretty much what I have today, and I'd like to learn feedback from you. And this is something that I'm currently working on, and I'd like to hear your comments. Thank you.